Hello everybody, and welcome back to page 37 in the workbook. We are ready to make our list of shortcut formulas for taking the derivatives of functions. Okay, what this is going to be is a list of common functions that tend to come up over and over again in our course, and what we're going to do is to write down a way to take the derivatives of these functions in just one step, or maybe a couple of steps, a much shorter way of coming up with a derivative than going back to the limit definition. Okay, so let's just look at these one at a time here, starting with number 1. So d dx of c, let's first remind ourselves what that notation means. That's just asking us to take the derivative of the constant function c. So you look at that c, you want to think of that as being a constant. And to maybe help you visualize this, let's think about a specific example here. What if c were equal to 1? Well, what that would be saying is that we're asking, what would the derivative of the function f of x equals 1 be? Well, what does the graph of that function look like? Okay, f of x equals 1 is a horizontal line, and remember that the derivative is about slope. What is the slope of a horizontal line? It's equal to 0 everywhere, and so if we take the derivative of a constant function like f of x equals 1, we have to get 0 because the slope is 0. So that means then that anytime you take the derivative of a constant c, you're going to get 0 because of that slope being 0. Right? I'm going to also put that into words. Okay, formula 1 just tells us that the derivative of a constant is always 0. Okay, and we come to formula number 2 then. Okay, so what if we want to take the derivative of a function that looks like x to the n, okay, where n is a constant? Turns out you can take that derivative in one step by just writing down nx to the n minus 1. This formula has a name, it's called the power rule. And you want to remember when you look at it, what's very important is that n is constant. This is a formula for taking the derivative of x raised to a constant power. Okay, and I want to illustrate just how that works with a couple of quick examples here. So suppose I gave you the function x to the 5th, let's say. There's x raised to a constant power. Okay, well, this rule says that we can take the derivative in one step by just first noticing what our power is. Okay, that's the n. Okay, n is 5 in our case. And so the derivative is going to be nx to the n minus 1. So that's going to be 5x to the 5 minus 1. Okay, since n is 5. And simplify that, you get 5x to the 4th. There's the derivative of x to the 5th. Okay, notice we didn't have to write a whole lot. That was pretty easy to do. Okay, let's look at another example. What if we started with x to the 1/2 for our function? Okay, well again, that's x raised to a constant power. This time the power is 1/2, so that's our n. And so taking its derivative, we would get nx to the n minus 1. That's going to be 1/2 x to the 1/2 minus 1 this time. And if we simplify that, 1/2 minus 1 is just negative 1 over 2. And there's our derivative. Okay, so you can see this is a little bit unusual the first time you see it, but we don't have to do a whole lot of work to get a derivative. We just have to kind of follow this formula. Okay, and you might be asking at this point, where does this formula come from? How do we know that we can take a derivative in one step like this? Okay, well, basically it goes back to the limit definition. Okay, so somebody at some point to come up with this formula had to write down the limit definition for the derivative of x to the n, go through a bunch of algebra, and what comes out after you do the algebra is this nx to the n minus 1. If you're curious to see that, you might Google power rule proof, for example. Okay, if you Google that, you will likely find a lot of videos, maybe also some text that shows you where this formula comes from if you're interested. Okay, and continuing down our list, what if we wanted to take the derivative of a function that looks like a to the x? Okay, where a is constant. This is called an exponential function, and its derivative turns out to be a to the x ln of a. Again, I'm kind of just showing you what the formula is. It can actually be derived using the limit definition in algebra if you want to. Okay, and then we come to a formula that's going to come up a lot in our course, e to the x. And e to the x has a really nice derivative. Turns out if you take the derivative of e to the x, you just get e to the x. Same function right back again. Okay, and the last three formulas on our list are kind of statements about derivative operations, you might say. So number 5 says, what if we take the derivative of a constant c times a function? It just tells us that we can pull the constant out and then take the derivative of f, kind of break it into 2 steps in that way. Okay, 6 says, what if we want to take the derivative of the sum of 2 functions, f of x plus g of x, and it says that we can break that into 2 parts. Just take the derivatives of f and g separately and add them together. Okay, and then 7 is similar, just with differences. The derivative of the difference, f minus g, is just f prime of x minus g prime of x. Okay, so there's our list. And again, what these formulas all have in common is they give us a nice, easy way of finding the derivative of a function just in a very short way, in 1 or 2 steps. Okay, let's maybe illustrate with one example to conclude the video here. What if I gave you a function that looks like x to the 4th minus 2x cubed? Okay, what would the derivative of that look like? Okay, well, notationally, h prime of x is just d dx of x to the 4th minus 2x cubed. That's just notation for take the derivative of x to the 4th minus 2x cubed. And if you look up at our list, formulas 5 and 7, they kind of apply in this situation. They tell us we can break this derivative down. Okay, in particular, we can first take the derivative of x to the 4th, then we can factor the 2 out and take the derivative of x cubed. Okay, and so to finish this calculation, we need to take the derivative of x to the 4th. So looking at the list of formulas above, do you see one that matches that situation, x to the 4th power? Notice that that matches formula 2, x raised to a constant power. Okay, and so we know that we can take that derivative by just using the formula nx to the n minus 1. In our case, n is 4, so we're going to get 4x to the 4 minus 1. Okay, and then we come to the derivative of x cubed, same idea. This time the n is 3, and so the power rule tells us that we're going to get 3x to the 3 minus 1. Okay, and if we simplify, that's going to be just 4x cubed minus 6x squared. Okay, and there's our answer.